Hello everybody. We've reached our last section in chapter 5, and this is a short little video here, but I just want to talk a little bit more about empirical probabilities. So make sure your cell phones are put away and you're ready to go for the next few minutes. Like I said, this is a pretty short video. What we're looking at in this section is how we can use simulations, and for us that's going to be StatCrunch, but it could be other technology, simulations to calculate empirical probabilities. So remember what we mean by an empirical probability. We've been focused on theoretical probabilities in the last couple of sections, but an empirical probability is a probability that's based on observations of a real, we'll say a real life event. So, for example, in sports, we see empirical probabilities all the time. A baseball player's batting average, for example, that would be an empirical probability. Percentages of times that a bus arrives late. Really, any percentage out there that you hear about in the real world, the percentage of a particular disease occurring in a society, any sports statistics, those are all empirical probabilities. When we can't find data or a situation is too complex for us to find the theoretical probability, we can sometimes simulate the situation and generate data so that we can calculate an empirical probability and use that to estimate the theoretical probability. So in this little example here, I've got a probability distribution table, and I called it example 2. It's really, I guess, just example 1. We know the theoretical probability for rolling a 6-sided die. So remember what this is a distribution table. We've got 6 possible events that it could land on: 1, 2, 3, 4, 5, 6. What is the probability in theory of each of those events occurring? So the probability, if it's a fair 6-sided die, of rolling a 1 would be 1 out of 6. Probability of rolling a 2, 1 out of 6. Probability of rolling a 3, 1 out of 6. You get the idea. Probability of rolling a 4, probability of rolling a 5, and the probability of rolling a 6. A couple things I want you to notice here. Each of these probabilities is less than 1. They all happen to be the same. However, in the real world, that may not necessarily happen. But in theory, that should be happen. They should all be equally likely. And the sum of all of these events, if I were to add those together, 1/6 plus 1/6, 6 times, right? Let's see, 4, 5, 6. That would be 6 out of 6, which would be 1. And that should make sense because all of the different events should add up to 1 in a given sample space. All of the probabilities should add up to 1. So have this in your notes. We're going to come back to this tomorrow. We're going to do some simulations in StatCrunch, and we're going to compare it to what we're getting for the theoretical probability. So we'll come back to this tomorrow. But the last thing I want to mention here is something called the law of large numbers. And the law of large numbers says if we were to repeat this experiment or this simulation a large number of times, in theory we want it to go to infinity, right? We want to do this an infinite number of times. We want to roll the die. In theory, an infinite number of times of rolling that die. What the law of large numbers says is that if we repeat this scenario a bunch of times, and by a bunch of times, like I said, a long time, thousands and thousands, the empirical probability that we're getting of an event is going to be close to its theoretical probability. So the more times we repeat an experiment, the closer our empirical probability will get that we see to what should happen in theory with the theoretical probability. And that's related to this example I just gave you above. So tomorrow in class, bring your notes with you, have this table filled out, and we're going to run some simulations in StatCrunch and see how these compare and look at the law of large numbers to see an example of what we're talking about. So I'll see you in class.